Welcome to today's webinar, Advanced Fixture Design with AC to DC Light Engines. I'm Carrie Meadows, Chief Editor of LEDs Magazine with Endeavor Business Media. Thank you to ERP Power for supporting today's presentation. Make sure to submit your questions or contact us with any concerns using the Ask a Question function on the left of this platform. You'll find additional downloads in the Resources section. Please turn off any pop-up blockers in your browser. And all registrants will be emailed when the webinar is archived on demand. Today's speaker, Vachik Javadian, serves as the Vice President of Applications Engineering at ERP Power, which has received a 2024 Bright Star Award for its TWM1 module with Bianco technology. Welcome back, Vachik. The floor is yours.
Thank you, Carrie. Well, first of all, I'd like to thank everybody for spending an hour with us. And I promise you this is going to be a jam-packed webinar with a lot of information. As the title suggests, it's a fixture design. And a fixture design, as you know, includes like thermal design, electrical, mechanical, and optical. And I intend to cover all of it in conjunction with ERP TWM modules. And I'm not going to spend a whole lot of time on the modules themselves. The majority of the presentation is going to be talking about those four elements. So as they say, tighten up your seatbelts and be ready for a lot of information. And another thing I'd like to mention, I might be going a little bit fast, but these materials are going to be there for your download, and you can review it again. Some of the sections, especially the mechanicals, you might need some review later on. So with that, I'm going to move into just a couple of slides talking about the modules themselves. So TWM stands for Tunable White Module. It is a highly integrated puck that includes the driver, and in this case, TWM1 and 2 have 3 channels, but we've moved on to even color version of it, which has 6 channels in one puck. In a small puck, we'll talk about it a little later. So these modules cover a wide range of CCTs, starting from 1800K, which looks like a candle, all the way to 6500, which is bluish color. And it also has numerous features like warm dim, and even the warm dim, you can put it in halogen or incandescent mode. And you can also select the maximum lumen output and set it to even lower or mid-range. And we'll talk about that later with the app. Also, these are dimmable with 0 to 10 triac ELV, and even the color module, we use DMX. And these are tunable CCTs with 0 to 10. So you can use external dimmers. For CCT dimming, you'd be using 0 to 10. And for intensity, you could use triac ELV or 0 to 10. And the light quality is fairly high. We address like 90 plus CRI applications with 2-step typical and maximum 3-step. So this, you can think of it as like a museum quality light. And again, as I mentioned before, we have configuration in Programmer or in the Bluetooth app, and you can configure numerous elements. I'm going to show you a screenshot of the app later on, but the minimum, let's say, would be your CCT, lumen, and the whole bunch of other features that we'll talk about it. So these modules get rid of the driver. And so if there's a JBox, you can actually get rid of that as well. And it is very easily replaceable in the field. So that is one of the main advantages of this module. We do offer non-Bluetooth versions, so not everybody needs Bluetooth. For lower cost purposes, we offer that. And also you could have it with or without the diffuser. And I'll talk about optics quite a bit, and you'll see why we offer that, both options. And mechanically, we offer side or bottom leads. Obviously, different applications are going to need different versions of these. Dimming performance, you can go 100% to 1%, and in some applications lately, as you know, dim to off has been popular, so we support that as well. And there is another feature that we offer in the app that you can set trims. Aside from maximum setting, you can even set the minimum. So you could define basically a range of CCT and intensity. There is an onboard thermal fold back, so you can't burn it even if your thermals are not good. It's going to fold back and reduce the current such that it'll cool it off. Later on, we're going to offer circadian rhythm, and this is, we have the hardware already there, and we just have to develop the app for it. All right, so the benefits, real quick. Number one, it lowers the system costs with a big margin, and at the same time, it offers high quality of light. And for a lot of manufacturers, it minimizes number of SKUs. So some people or some customers of ours, they have like hundreds, if not thousands of SKUs of the fixture. So you can minimize that dramatically. And design is simplified, and I'm going to go through that in a lot of details. And most importantly, this is something that we hear from our customers. Actually, they brought this up over and over, that this is going to address the field configuration. Let's say the fixtures are installed, you can still go ahead and modify, let's say, the CCT, intensity, and a whole bunch of parameters. Or later on, if it needs to be replaced, easily, just like a light bulb, can be taken out without knocking down, let's say, drywalls and things like that. So applications, this can go almost overwhelming majority of the fixtures out there, but just kind of give you some examples, but these are not limited to it. So general illumination, downlights, and God knows how many hundreds of variations of that exist, pendants, architectural lighting, spot, track, accent lighting, low bay, and even high bay with some of our latest high lumen modules. These are all possible. So with that, let's dive into retrofitting and modifying your existing fixture or coming up with a new fixture altogether. So process of converting your existing fixtures, that is what it's called retrofitting. So that is what we mean by retrofitting. And ERP light engines, as you can see in the picture, it basically embeds or includes the driver. It includes the LED or the COV, and the driver itself, as we talked about, depending on if it's a single channel or it could be up to 6 channels. So think of a 6-channel driver already within that small puck. And that puck, as I talked about it, it could be like 65 millimeter on TWM2 and 50 millimeter on TWM1. So all of it is going to go into a small puck, and all of this is going to reduce the overall system cost by integrating all these functional blocks into the same module. So let's talk about retrofitting itself, and we classify it in 2 different categories. Number one, either you retrofit the existing fixture as it is and embed the module in it, or design it from scratch. So each one has its pros and cons. So if you go take your existing fixture and try to retrofit it, essentially using these modules, it's going to be much quicker time to market because you're not designing the mechanicals, heatsink, and all that stuff. So all of it will remain the same, and you'll just use the module instead of your LED and the driver that you already have. So obviously the development cost is going to be lower, and quickly you can turn that around. Below I have a bunch of pictures. As you can see, the center big picture, I don't think you can see my mouse, but there is some of these white fixtures, especially, they have this big block at the end of it, and those are the housing for the driver. So all of that can be, as it is that we converted, those are empty now. In a retrofit case, those are going to remain, but if you do a design from scratch, all that whole box will go away. So showing you on the right-hand side, those two pictures are the color modules. So these are the AWM modules. So it has full RGB plus white, which is tunable. So you can think of it as a white module that is tunable and a color module all in one. And this is our latest development. We call it AWM. I'm going to go through a lot more detail. The ones on the left, the green one, essentially we're using like different technologies. Could be, let's say, TWM or CWM, and then we also use a single channel version, and that's called SWM. I'm going to go through a lot more detail later on. So now the cons of using a retrofit approach is that because you're using your existing fixture, the housing is going to remain the same. As you can see on the right-hand corner at the bottom, that whole housing is base of a fixture, and that was basically housing the driver. And the driver itself, you could see that it's a big chunk, heavy, and also in this particular case, because it was a color module, so it was using like multi-channel driver. I'm not saying there's anything wrong with it, because that is how the fixtures are designed right now. But with the modules now, this whole base can essentially go away. And also, I mentioned like lower cost. I'm not going to obviously, I'm going to let the sales guys talk about pricing. If you need, you can contact them. But to kind of give you an idea, a multi-channel, it's especially for color, a driver costs about like $80, $90 or so. And the cost of the module is going to be a fraction of that, which includes the driver. And a fraction, what I'm talking about is, let's say, 1/3 to 1/4 of that. So you could see the cost saving just by the driver alone, not counting getting rid of all that bulky, let's say, housing, all that aluminum, the weight and the size and everything else. So the same concept holds true. Think about the picture on the left. Also, that housing will go away, or on the one, where at the top you see the housing where the driver sits. All of that can go away. So the cons of it is, if you go with this approach, is that you cannot fully take advantage of the size reduction because you're sticking with the existing fixture. So that is the con with going with the existing mechanical design. So the second approach is that you want to do the design from scratch. Obviously, when you do the design from scratch, you're going to take advantage of that everything that I've talked about, essentially getting rid of that housing, and most importantly, you're going to come up with a lighter and a smaller fixture, which is aesthetically pleasing, and the material cost is going to go down, your shipping cost is going to go down. But there's a con to it. Obviously, because you have to do the mechanical design from scratch, your development time might be a little bit longer, and cost might be higher because you have to design a new body for it. So those are the pros and cons of these approaches. So let's dive into the system level design consideration when you're dealing with a light engine. So as I mentioned before, your system design will dramatically be simplified, but you can't ignore laws of physics. What I mean by that, you still have to think about the thermal, the electrical, optical, and mechanical designs. There's no way shortcutting that. So our various modules, we came up with multiple versions of our modules, and I'm going to go through a lot of details. They do provide high quality of light, and they have different characteristics, and namely the maximum lumen, the CCT range. Does it support, let's say, warm dim, dim to off, or does it have high LPW efficiency, that is lumen per watt, and the size of the LES? All of these matters, and I'm going to expand on these when I get to the optics section. Does it have Bluetooth or not, or any other features? So all this has to be considered. And essentially, each fixture manufacturer, we expect that they'll have their own unique optical, mechanical, thermal design, which will offer a distinct product and basically provide it to the market. And that is where, I mean, we're not obviously the fixture manufacturer, but we're going to help fixture manufacturers to design it in, and fixture manufacturers will decide the specifics of their fixture. And one other thing about the integration of all the features that I talked about is that you don't have to go back and do the, review the LM80, come up with L70 and do all those tests and provide, let's say, driver lifetime and all that stuff, because we already embed all those and we test it and characterize it. So based on your TC, we'll give you the, let's say, 50,000 lifetime if you meet that certain criteria, which is about 75C. And I'm going to expand on that later. So ERP light engines enable designs that previously weren't possible because of some of the things that I just talked about. And it does have a rich set of practical features that conventional fixtures may not have, may or may not, depending on the cost structure. And the high quality of light and static and mechanical, due to the fact that it's miniaturized, essentially gives fixture manufacturers a lot of freedom on the mechanical design. And all of it is done at a lower system cost. So let's dive into those 4 major parameters that I talked about. As you know, every fixture design, I mean, I had to cover all of these because in a fixture design, you cannot do any design, regardless what kind of a technology is being used, without doing the thermal, electrical, mechanical, and optical design. So I'm compelled to cover all of it, and which is related to ERP light engines. And each one of them, I'm going to go through the essence of it or the important aspect of it, rather than making a separate seminar or a webinar on each one. Although each one of these sections, I have done specific webinars and seminars, but I essentially condensed it and brought up the key factors that ERP light engine designers should know about and they should apply. So if you essentially absorb and use this material as a reference, you have pretty much everything you need to design a full fixture. And just as I said, use this material as a reference, and this is going to be a very good guide for you. So on a thermal, obviously you don't want to do all the designs which I've seen over and over, that the thermal design becomes like an afterthought. And it has to be thought of right from the get-go. Actually, to me, thermal design is the primary factor that determines everything else. Your lumen output, efficiency, cost, and a whole bunch of other things. So you have to think about it right from the get-go and get it as part of your design. So the second sentence pretty much defines and suggests what a thermal design, a good thermal management should be. That should include reducing the total amount of generated heat, essentially called thermal load, and effectively conducting it away from the heat generation source, which is driver and LED, which in this case, LED are POC, the modules, combines them both, and you want to conduct it to the ambient air as effectively as possible. So I'm sure you've seen it over and over, even our thermal simulations and thermal seminars that we brought up. The thermal performance is the primary factor that predicts what the lifetime and, more importantly, the reliability of the fixture. So don't think about, let's say we say, keep the TC 70C or 75C. My recommendation is keep it as low as you can, because that determines your reliability aside from the life itself. So you don't want, the cooler it is, the more reliable, less field failure you're going to have in the system in the future. So as I briefly mentioned, your thermal design is going to be basically dictating the amount of light output and efficiency, even the cost of the system, lifetime, and reliability. So it is the primary dictating factor. If it's ignored, I mean, you're going to get a pretty lousy fixture, and you're going to have high rate of failure and all sorts of problems in the field. And nobody wants that. So please pay special attention to the thermal design and all the key points that I'm going through. So lifetime of a driver, which exists in our modules, is typically controlled by the life of the electrolytic capacitor. And basically what happens, think of it as there's a little bit of moisture in the capacitor. So if the temperature is high, essentially that moisture that makes that conductive material inside, the charges pass back and forth from positive to negative, that is going to degrade, and after a while, your system is going to malfunction. And that is how the lifetime is defined. So life of the electrolytic capacitor is half, or let's say 50% for every 10C increase in the temperature. And as you can see on the left-hand side, essentially you have like exponential decay as the temperature increases. That is the life keeps going down as the temperature increases. And the graph on the right shows the capacitor, and it's a logarithmic scale. So if you have an exponential decay, it turns into like a straight line. Essentially, the concept that I just mentioned, that the life is half by increasing the temperature by 10 degrees C. So every 10 degrees C, you can cool off your system, you're doubling up the life. Just think of it that way. All right, so let's move on some of the thermal parameters and thermal conductance and parameters that are important. So thermal contact is one of the very important factors, and especially in conduction, as one of the modes of conducting heat away is the conduction, and you could see the equation. I'm not going to go through the equation, but once in a while, I'll point out the key parameters there. So what you want to do is apply a thermal grease, or you could have like gap layers, very thin, very conductive, but thermal grease is good enough, and Arctic Silver is a good brand. We're not advertising that, but just try to use a good quality material. And the key thing is that you want to apply as thin as you can and as evenly as you can. So these are very, very two key parameters, and I show pictures there. So the one at the bottom left, I've seen like some people put a big blob and then tighten up the screws, and so what happens, you're going to have only a small percentage of bottom of the module making thermal contact with the heatsink or the chassis, and the rest of it is basically as if it doesn't exist. So that has like two parameters there. Number one, which I highlighted in red in the equation, A becomes reduced, so your conductance is going to be reduced. Another thing, delta X, which is the distance that the heat has to transfer, is increased, meaning that you put a big blob there, heat has to transfer travel a longer distance, so your conductance is going to be jeopardized by two parameters. So that is why you don't want to do this at all. The same thing applies to the second one, which is a cross pattern. Exactly the same parameters play, and the conductance is going to go to almost nothing if you apply that. The third one is what you want to do, and the picture on a circle that I show, it's the very, very thin. You almost have to see the aluminum at the bottom, and extremely thin layer, and tighten it. Another very important parameter is not using double-sided tape. That is an absolute no-no with the modules, because you're going to have very, very horrible result and failure, or the thermals are going to be basically throttling back. You're not going to get the lumen out, and the life of it is going to be tremendously affected. So as you can see on this picture, although I have a driver, so what this does, notice the total surface that it's available to conduct heat away. Number one, you're using only maybe 20% of it. And then secondly, it is a thick layer. Notice again this conduction equation. Area is dramatically reduced. Let's say you're using only 20%, and the distance is also increased, and the K factor, which is how conductive it is also poor. So your conduction or the amount of heat transferred is going to be dramatically lowered. So consider this as an absolute no-no, and we're not going to even honor the warranty if somebody uses the double-sided tape. That is how bad it is. So let's just move on. And another point I want to show is that if you keep the screws loose when you tighten up the module, you're going to have a much worse result. As you can see, long time ago, we've done like an experiment. So we have exactly the same light modules, and one of them we keep it loose, the one that it's red. And this is a FLIR camera picture, and on the left I show like there's a 34°C difference from the red one to the ones that are nicely tightened up. So think about it. 30°C essentially is going to give you like you have it and you have it again. So 1/2 to 1/4. So life of the module is going to be 1/4. Let's say if you have like, for example, 40,000 hours, now suddenly you're going to have a 10,000 hour life if the screws on the top of the module is not tightened up properly. So the next thing about convection, so this is another mode of heat transfer. As you can see on the bottom right-hand corner, essentially you conduct the heat away from the fins to the ambient air. So what you want to do is expose the heatsink, the chassis, to the ambient air. That is how the convection works. And just because of that point that I just mentioned, if you have the heatsink enclosed in a chamber, let's say in a cylinder or a box or whatever, that heatsink becomes very ineffective because that air, that hot air, does not move to the ambient air effectively. So just always think of that. Whenever you have a heat from the LED, from the driver, from the module, you want to expose it to the ambient air as effectively as you can. So one of the ways to improve it, you want to increase the airflow by the fin design, spacing them out, create holes, or create gaps if you have like blades. Those are the kind of things that it's going to improve the convection, because the airflow is a very important factor for convection. So in some designs I've seen, which I don't recommend at all, people use like fans. It does a very good job in airflow, and the convection is going to work really nice. But the problem with that is that the life of the system depends on the life of the fan. And as soon as the fan dies, that thing is going to burn down. So just be super careful with the fans. Okay. Now, to make life easier on design community, what we've done in our app, which is what we've developed, and it's freely available to all of our users, we've included the microcontroller temperature right on the app. So in this case, you could see where I have that yellow oval shape. It constantly reports the microcontroller temperature. And just as an example, I've given you delta in this particular case with, let's say, TWM2 and TWM1. What is the correlation between the internal microcontroller TS and the TC? So TC on modules, this is another point that I'd like to bring up. It is measured right at the edge, right at the bottom of that aluminum. And as you can see in those two pictures on the bottom left, the probe right at the corner, which shows what the TC point is, that is where it is connected, and that is what it's measuring the temperature. So the delta I'm talking about is the microcontroller data that is reported on the app, and the actual TC measured on the module right where it connects to the heatsink. So the point is that when you have one of these, in your system, your heatsink is going to be different, the chassis is going to be different, the airflow is going to be different. Once you define what that delta is, then all you have to do is look at the TS, basically let it stabilize, let the temperature stabilize. Some fixture could be half an hour, larger ones could be, let's say, an hour, and then read that TS, and it'll tell you what the TC is. You don't have to measure again once you know that. So In order to, let's say you do the design and you figure out that your TC is higher than, let's say, 75C, because with 75C at TC, we give you 50,000 hour lifetime. And if you need to lower that, it means that you have to improve the heatsink thermal resistance. And the way you do it is to increase the size or use a heatsink with a better RTH, and or the area, the fin area, and or the number of fins. So all of these, you can look at the data sheet of the heatsink manufacturer and you can pick up the correct one. Another thing you can do with the existing heatsink is to improve the airflow. And there's a lot of tricks, as I said, spacing them out, drilling holes, and there's also all sorts of other tricks you can do. If none of these work, let's say if you're stuck with a specific size, heatsink, and whatever, another thing that you must do is just lower the lumen. For example, if you're pushing, for example, 4,000 lumens out of that module, then you might have to settle for, let's say, 3,500 or 3,000 lumens, and that will lower the temperature such that it'll give you that 50,000 life, essentially bringing the TC below 75C. Okay, let's move on. So there's a ton of CFD, which is computational fluid dynamic tools out there. Those are pretty sophisticated and sometimes very expensive. Some of them are like Autodesk, SolidWorks, Cadence, and a whole bunch of them out there. But for this purpose, you really don't need to go down, that level. I found this, simple simulator, from Novell Concept. One thing I like about it, that it gives you the airflow. Right at the top, notice there's an airflow. I don't know, this might be a little bit of an eye chart, but the only thing that or the main thing that I changed from the left to the right is the airflow, essentially increase the airflow. And even I shortened the fin size, so that's another thing that I changed. Essentially, the thermal resistance from 1.1 goes to like 0.3. So like 1/3 of the thermal resistance just by increasing the airflow. So again, you can play around. I'm just giving you an example and give you the concept, how you can play around and figure out exactly what you need to perform or to produce the lumen that you need. So it'll tell you the size of the heatsink you need, and then you can implement it in your fixture. Okay, let's go through the next parameter, electrical, in the system level design considerations. Truthfully, you don't have to do much on electrical design. All you have to bring into system is the AC power. Could be basically 120 volt or 277 or anything in between. As I showed you on the first page, this is like a universal input, AC. So what you need to do, once you define your output lumen, essentially, without you knowing, you essentially defining what the drive current will be, and then considering your thermal limits and LPW, you can control the output lumen out of a module. So this is like a trade-off that you have to go through, and I'm going to give you a little bit more information later on how to select the correct vehicle for conducting or implementing the fixture that you desire. So no need to say, this is LED 101, lower drive current will increase the efficiency and LPW, lumen per watt. At lower lumen, basically you drive current goes down, efficiency goes up, but your lumen obviously is going to go down. That is at a given LED design. You can always increase the number of LEDs. So that is another way. If you need more lumen, higher level of lumen, you can obviously add the LEDs as well. That's another approach. So light engines can be configured. I think I briefly mentioned you can configure it in our programmer or the Bluetooth app. As you can see on the right-hand side, we have a slider for the intensity, and then also a slider for the CCT. So also on the left-hand side of both of these sliders, there's a trim, and that trim actually is pretty unique that you can define the minimum and the maximum. It is not only the maximum that you can control. You can always control the lower lumen as well. Let's say you have a kitchen. For example, in the kitchen, you don't, let's say housewife or the cook, may want a specific range of brightness. So with that, you can go ahead and fine tune it. Or let's say bedrooms is another place that this could be pretty sensitive, or the work area. So you can utilize the tool and set the entire range. So these are some of the flexibilities available in our app that you can download from the App Store. Okay, so let's move on, mechanical and aesthetics. So this is a very important aspect of the design. As I alluded to it, a small size light engine totally eliminates the driver and driver chamber, which is very important. So altogether, you can wipe that out. And also the J-box, but the J-box, actually I'm going to talk about that later. Let's hold on to that in the next couple of foils. Essentially, by getting rid of that base, yield smaller, slicker fixture design that previously was not thinkable. And I've seen a lot of slick design because that is very common now. It just gives, let's say, architectural designers especially a lot of freedom to come up with the fixture, because when you have that bulky driver and the whole engine and the heatsink, artistically, there's not a whole lot you can do, but with these modules, designers have a lot more freedom. So essentially yields lower weight on volume, saving on shipping and installation costs as well. So another point that we intentionally did on these ERP drivers are that these are top mount. So essentially this turns into like a light bulb design. So notice on the picture on the right-hand side, those two screws that I'm showing the cross-section. So that basically gets connected to the heatsink. On the left-hand picture, you could see that two screws mount the module to the heatsink, plus the holder as well. The reflector holder also uses, so one set of screws tightens down the holder, the module to the heatsink all in one. Okay, so with these, when you have a top mount, the entire module, which includes the driver, it is exposed, and once the fixture is all built in a wall or something, you don't have to rip out the drywalls, let's say 5 years, 10 years down the road. If somebody wants to change it, or let's say it's a white module, if somebody wants, let's say, even a color version or a different variation of this, you don't have to rip anything up. Essentially two screws will just open up and you can replace the module, and there you go. So this is very important, and a lot of our top customers mentioned about this, that it's been very helpful. So this section, this new, I have like a few foils about this. Think of it as a reference material. Again, we have a lot of customers asking about UL and mechanical considerations. Obviously, I'm not going to go through all the details, just you can use it as a reference. So we came up with some like generic fixtures. Again, think of it as mechanical engineers doing fixture design. So think of this as, let's say, a downlight, but this is not like any downlight. So you can like class of downlights, let's say. It's a generic design. All we want to show is how you do the mounting and isolation and conduit. Notice that, again, you don't need to have the J-box, but a lot of our large customers told us that, yes, electrically and by code, we don't need it, but electricians and installers, they're used to doing designs or doing basically installations with the J-box, and that is why, although it is not needed, they put it in there because they're not going to be able to train God knows how many thousands of technicians, electrical technicians, that all their life have installed fixtures with a J-box. So that is the reason that it's there. So notice there's a conduit, basically electrically isolated. There's a metallic. So this is what probably UL is going to require you to do. So as I mentioned, it's a mechanical example for UL consideration. So this is really what we want to convey here. So the next one, so this one was for like new construction modules. So think about it's a new building and you're going to have a new installation or a new downlight. So the second one is a remodel. So the fixture is already there, the can is already there. And so this model of design is exactly for that. So this is pretty much the same pictures that I showed you. So there's a module, and it could be any one of our modules, obviously. Then you have the heatsink, and then you have the heatsink mounted and the reflector holder mounted, and then you're going to have the reflector mounted, and then the top cover lens. Essentially, you're going to have the fixture right at the bottom right corner. And then, so this is the overall fixture. This is how it's going to look. Again, put it in a cylinder. Just don't think about that as the only fixture. Obviously, again, think of it as a generic fixture. That could be anything. You can think of dozens and dozens of styles of fixtures out there. But on the bottom right-hand corner, that is how the fully assembled fixture will look like in a remodel case. So the third one, again, this category, I don't want to say I invented, but think of it as a light bulb, and that covers God knows how many, let's say a desk lamp or a pendant probably could be a good example, or class of fixtures that are in that category. So this is how it's going to look. Again, all of them typically have some sort of a canopy up there on the ceiling, but this canopy really doesn't have to exist at all, because there's not much there. So electrical wires can come in and can go to the cylinder, and the connection can be done there. But obviously you can have let's say a 1-inch canopy right at the top. Doesn't have to be big because there's no driver, no nothing there. All you need to do is maybe a wire nut, so as we show on the middle picture. So these are, just think of it as some guidelines and help for top-level design and dealing with UL. So in optics, I think in the previous seminar, we provided these. So we have already a few holders for reflector for, let's say, little and nada, namely for Angelina and Angela, spot, medium, wide, for all three of them. They're available, so nothing special. So you can order these from ERP. And there's a ton of reflectors that you can mount. There's no magic here. I'm not going to spend any more time here. So the other optical support parameters, so you can use for TWM1, which is Zaga compliant. You could use the existing holders that are available from various manufacturers. So this one is little Hekla. God knows how many hundreds of optics you can put on it. And this is one example. So this is a TE Zaga compliant holder that we use from one of our customers with their own lens. And so you're right in front of them. We just put our TWM1 and connected it, and boom, you have the fixture. So again, I'm not going to go through any detail. But also you can customize things and come up with your own. Let's say we do this plastic. If somebody has their own custom optic with their plastic holder, we do this holder or the top plastic that you can mount this existing optics with the holder. So, okay, now on the human eye, basically think of it as a sunlight. This is the spectrum that we could see. And what I want to point out that our eye has a filter, and this is basically the shape of the filter, and essentially the green light we see much better than the other ones. So blue light we don't see much, and that is one of the reasons blue and the once you go to the deep red, our eye does not see anymore. So this is the whole spectrum, electromagnetic spectrum, and we see a very, very tiny area of that. So that is actually one of the reasons when you do color mixing, you're going to get a lower efficiency because our eye doesn't see blue. And when you do, all the LEDs, could be COD, regular LEDs with remote phosphor or non, essentially what they do is they convert the blue light to white light such that our eye can see. Because, you know, if you have the same amount of energy, the blue light, we're not going to see much, but once it's converted, it's going to turn into, you know, something that human eye can see. So we have to improve the optical design. All I'm saying here is, without going too much detail, is that if your optical efficiency goes from 90% to 60%, your thermal load or the power goes 50% higher, and the number of LEDs you need to use is 50% higher. So LPW goes to hell. So bottom line is that optical design is one of the most important parameters to make sure that the light is not being wasted. It is not that easy, but it's something that you have to think about, and that is going to be the determining factor how efficient your system is. So to summarize that, what you want to do is optimize light extraction, and may or may not use diffuser reflector, and you can design a custom setup. And a single optic as close as possible to the LES, or the light emitting surface of the LED, is going to yield the best desired pattern, light distribution pattern, and LPW. Basically, your system is going to be more efficient. And another thing that we've seen, as you can see on the bottom two pictures on the right, match the LES with the optics. So always use equal or smaller LES than optics itself. It could be lens or reflector and the bottom diameter of that. So if you have a wide LES here and you use a small optic, essentially you've thrown away a lot of light and your efficiency is going to go to very, very low. So I showed like from 90% going to 60%. I've seen designs like 10% efficiency. So 90% of it is being wasted. So just be very careful about that. So another thing that our modules do, it addresses a major concern of the architects. Essentially, architects don't want to have different colors or different shades of white in the same area. And that is, I mean, you can imagine how unpleasing that is. Let's say if one has like I'm not even talking about different CCTs. I'm not even talking about different CRIs. The same CRI, the same CCT from different manufacturers are going to have different shades of the color. So I'm not going to go through the color science there. There's a good reason for that. So, but using one light engine and with variety of lumens, it's going to give you the same quality of light, and you could have multiple fixtures designed by it. So use the correct vehicle or the light engine to perform the specific function that the fixture is being designed for, and most efficiently, essentially highest LPW and the lowest cost. So what I want to do in this next section is basically show you how to fish rather than giving you a fish. Because as I said, we have multiple fixtures and multiple modules, sorry about that, that could be used in a variety of fixtures. So what I'm showing here is that these are like two different Ganyo results. So we started, let's say, with TWM2 with, as you could see, the light pattern is more like a Lambertian, fairly wide. But the most, the issue was that the LPW was like, this is, by the way, at the system level, not on our modules. Let's say the module was 100 LPW and they came up, let's say, about 79. But also the total flux was like 1400 or so, but worse than anything else, notice that the beam angle is like 92 degrees, which is fairly wide. That is like flood. So by coming up with another module, which I'm showing at the center, so we gave him another module with 120 lumen per watt, and even a smaller LES, let's say 12 millimeter LES, and the result, obviously they did some additional optics work here. So they came up with 100 LPW out of the system, and total lumen were like 1800, and the beam angle 25 degrees. As you can see, they achieved a very good result with this. Nothing stops us to give them even 140 lumen per watt. So let's move on. So we have TWM2 and TWM1. It's a 3-channel puck. So we use saturated LEDs. And CWM is basically 2-channel or 3-channel version of this. Essentially, think of it as a COD that has 2 channels, but the range of the CCT is 2700 to 5000, so slightly tighter, but it can give you more lumen and higher efficiency at a smaller LES. So if you want to push even further, if you have only a single CCT with a one channel, we can give you even higher lumen at a higher efficiency at a lower cost. So this is the variations that I was talking about. And AWM is the 6-channel version, so essentially it has white plus color. So you have 3-channel desaturated LEDs that can give you white, and then 3-channel give you saturated color. And so this diagram essentially describes the entire modules that we have today. So TWM1 and TWM2 are the core modules that we came up and we're in production with. And so if you go to the left, I call it like high density at the top. Essentially, we give you a smaller LES. So notice the center ones were like, we started with 32 millimeter, and the TWM1 can go, let's say, 19 millimeter LES. But if you go to the left, we give you 9 millimeter and 12. So as you saw in that example, it can give you a tighter beam angle applications. And then if you move to the right, which I call it high output series. So if somebody needs 4,000 lumen, 5,000 lumen, or if somebody needs even higher, we can come up with a higher lumen version. And these are the 3 series. So we can easily give you, even in the 32 millimeter, we can give you like 4,000 lumen out of the puck. So if you go hop, so from the center, again, from TWM1 and TWM2, if you need more features, namely color, you go to AWM. That's the 6-channel one. If you go down for the simplified version, as I talked about, the CWM would be 2700 to 5000 KCCT. Also, you can go to a single one, which is SWM. Okay? And that's pretty much what I wanted to cover. I want to give as much time for questions because that's important. But in summary, TWM modules, lower system cost, the high quality of light, integrates numerous high-end features in one simple compact module, eliminates hundreds of SKUs, simplifies fixture design, quick time to market, reduces field installation costs, and replacement is much easier, just like a light bulb. So with that, I'm going to go to Carrie and start answering questions.
Really great information and a lot of depth there. So let's get into some of these questions really quickly. What would be the thermal trip temperature for the light engine?
Okay, so that, internally we set it, obviously we want to cover like LEDs, we don't want to go over like 85C and 90C, so that is what we trip it at. So the TS, as soon as it gets around, let's say 90C, we're going to trip it. But in all practical applications, as I said before, you got to look at keeping the TC of your module. So you don't have to think about that. As long as you keep the TC of the module sub 75C, you'd be fine. But internally, that's how we trip it. Yeah, next question. Great.
Is the module UL listed, and is it Class P protected?
Okay, it is. We are going. We are in the process of going through UL right now, but it's going to be very difficult to do Class P because this is not a driver. Because it has the light engine and all that stuff. So I would say, think of it as a, just UL listed, and Class P is going to be very difficult to pull because of UL, because they're not going to treat it as just a simple driver. And then, as you know, Class P is just for drivers. Yeah, next question.
Okay. Understood. Could you give us the average lumen output of the TWM1 and 2, please?
Yeah. So just to give you I think let me show you actually the next. I'm going to go to the next. So this is part of the reference. So think of TWM2 about like 25 to 2600 lumen. And depending on TWM1, what the LES we go with, let's say 9, 12, and 19, you can go up to, let's say, 1800 or so on TWM1. But if you need higher lumen, we can go SWM like you could see like 5,500. The same kind of thing, about 4,500 on the CWM.
What about the maximum wattage?
Yeah, so maximum wattage, again, depends on the lumen and the efficacy of the puck. So TWM2, think of it as 100 LPW. So let's say about 24 to 25 watts. That is the maximum on TWM2. But you could go higher again. It all depends on the LPW. Let's say on SWM1, as on the example that I showed you, we go with, let's say, 120 lumen per watt. So just think about that. You can get pretty high lumen at a fairly low wattage. So all you have to think about is the LPW of each module and basically the lumen output. That is going to give you the maximum wattage that you get out of it. So think about, if you just do a quick math on that. I'm just going to give you just a quick, let's say if you go like 4,000 lumen with the LPW of, let's say, 120. Anyway, so you get like about 33 watts. So 33 watts on a 120. But we are coming up with even more efficient SWMs. As I said, we're just about to introduce the 140 lumen per watt version. So that'll, let's say, bring down 4,000 lumen at roughly about 27 watts. Okay, next one.
Based on the time that we have, I'm going to move to this question. You mentioned that installers or designers can remove the J box, but the fixture does still have to have a splice area for the building input line voltage. Is that correct?
Yes. So see, the module itself, it has the fire protection, which UL looks for. But also, whenever you bring in AC at some point of time, again, this is per electrical code, there has to be some protection there. And that is, you remember on the last, or I call it like pendant module, that one we still had a little bit of a canopy area, basically to do the wire knot or or whatever connector, Wago or whatever it's being used. Yeah, next one.
Okay. I think this might be our last question. Is the delta between TWM2 and the app reported micro TS showing that the TS is reading higher or lower than the actual TC?
Yeah, that's a very good point. Actually, so TS that is reported on the app is always going to be higher. And, just think about it. The heat sink is supposed to take the heat away and basically send it out to the ambient air. So always you're going to have TS that is reported on the app higher than the TC that it's on the heat sink or right at the edge of the heat sink at the bottom of the module. So, I mean, that is the whole purpose of heat sink. So internal to the module, which is the core of it, is going to be, let's say, the microcontroller. That area is going to be much higher than the TC itself. But by the way, if you see that the TC is higher, or I mean, you will never get higher than the TS of the internal micro. But if you see these are getting close, or it's a very, very small delta between them, that means your thermal design or heat conductivity is not done right. Either you don't have a good thermal contact from the module to the heatsink, or there is some sort of an insulator there that is preventing the heat to get out or being coupled to the heatsink. So that'd be a good indication. But as I said before, that delta is going to be very unique to your design. But you should always see that delta, and it could be, different values, or roughly, I mean, this should be like an average design. An average design, you should see somewhere in that range. But I just want to emphasize that it's going to be different depending on. So if you have a heatsink with a very, very good, let's say RTH, your thermal conductivity is very good. then you're going to have a much bigger delta because it's going to keep it cool and internal temperature is going to be higher. So, these are all good indications, and you should always watch for them. Yeah.
That was a
Okay,
great answer. I think that's all the time we have for today's webinar. We just hit the top of the hour. So many thanks again to ERP Power for making this presentation possible, and also to you, Vachik, for speaking today. You went into a lot of detail, and I think it's good that those reference slides are included at the end. Thank you so much to our audience for joining us, and have a great rest of your day.
Thank you.